Okay, we're going to open up a new topic, and this is acid-base chemistry. Acid-base chemistry may strike you as a topic that's more important for general chemistry or a topic that's more important in analytical chemistry. But as it turns out, it has big implications in organic chemistry as well. First of all, organic chemists are interested in very often in whether something's an acid or a base. But as it turns out, the types of skills you use to evaluate acid-base chemistry have a lot of overlap in organic chemistry. And really, it's for this reason that I'm a big advocate for emphasizing acid-base chemistry in organic chemistry. So let's look at just a simple, general acid-base reaction. Here is our acid, HA. We're not specifying what A is. It's just something that's attached to a hydrogen. And we're going to assume that we're in water, and the role of water is to be our base. It's going to accept the proton. And so this is going to engage in an equilibrium reaction. All acid-base reactions are equilibrium reactions. And what happens is the hydrogen on our acid, the proton will get picked up by our base, water. And that's going to form, since the acid is losing H+, this is a neutral species, the A group, whatever it is, must pick up a negative charge. Now you may look at that and say, how do I know there's a negative charge there? I haven't drawn enough of the structure for me to assign a formal charge. Well, if this is going to lose H+, the other part of the molecule must form an anion. Now, at the same time, that H+ goes on our water. And we're going to form H3O+. So here is, on the other side of the reaction, this is now our conjugate base. And H3O+ is our conjugate acid. So this is our conjugate acid because if we look at the reverse process, H3O+ is going to lose the proton and form water. So therefore, going backwards, this H3O+ is acting as our acid. Now, when we look at acid-base reactions, because we're moving around a proton, an H+, we are going to create charges. If we're moving charges, we're going to create charges. And the charge of note is this conjugate base. So we are creating charges and normally the species that we're going to find most interesting is our conjugate base. Not always, but normally this is the most interesting. And so when we look at this anion, this conjugate base, we then need to decide, very often in organic chemistry, how is the position of this equilibrium affected? So, we can quantify this with an equilibrium. Now, we're not going to run around calculating equilibrium constants. You might do that in general chemistry. We don't do it a lot in organic chemistry. But we still want to be able to judge, is this equilibrium favorable or not? Does it lie to the right or does it lie to the left? To do that, we're going to look at this charged species that's formed and try to decide, is this charged species stable or not? Because remember, the stability of either the right or the left determines the position of the equilibrium. So delta G equals minus RT natural log K. The stability determines the equilibrium. So the tools that we'll use to decide whether this anion is stable or not are the tools that we'll often use in organic chemistry, because we will regularly encounter different charged species. And so if we get comfortable in acid-base chemistry talking about the stability of charged species, we'll therefore be much more comfortable in organic chemistry when we also identify charged species, and we have to decide which one's stable and which one's not, because it'll help us pick out different pathways. Let's choose the pathway that goes through the most stable intermediate. How do we know it's stable? Well, we had practiced in the realm of acid-base chemistry, which is a little simpler, in my opinion, than organic chemistry. So by studying acid-base chemistry, we're going to be more prepared to discuss charged species in organic chemistry.